In section 6.2, we're going to look at various properties of binary relations. So the first property that we will look at is the reflexive property, and then the closely related anti-reflexive property of binary relations. So a binary relation on a set A, and here we're just looking at on a single set for all of these properties. So a binary relation is reflexive if, no matter what x you take from the domain, it's always related to itself. So for every x in the domain, x is related to itself. Okay. So to show that it's something, that a relation is not reflexive, okay, because this is a universal quantifier, the way that you can disprove a universal quantifier is just to find one single counterexample. So if you wanted to show that it was not reflexive, you just need to find one element in the domain where it wasn't related to itself. If you wanted to prove that it was reflexive, you'd have to make a general argument that it was true for every element in the entire domain, either exhaustively listing them for a finite domain, or for a large or infinite domain, you'd have to make a general argument. Okay, so let's look at some examples. Let's say we have a set that contains the integers 1, 2, 3, 4. Is this reflexive? Okay, so the relation where A is related to B if A divides B. Okay, well, it would be reflexive if, okay, for every element in the domain, 1, 2, 3, 4, the element would divide itself. So does 1 divide 1? Does 2 divide 2? Does 3 divide 3? Does 4 divide 4? Those are the questions we'd have to ask ourselves. And yes, it is true. So this one here, 1 divides 1, 2 divides 2, 3 divides 3, 4 divides 4. In fact, every element divides itself. Sorry, this marker is not very... Okay, and so it is reflexive. Okay, so let's say the next relation. So what an element is related, element A is related to element B if the sum of A and B is less than or equal to 3. So is 1 related to itself? Sure, 1 plus 1 is 2, which is less than or equal to 3. So 1 is related to 1. That works out. But is 1 related to 2? Okay. Sorry, I should put an R in there. Is 1 related, or sorry, is 2 related to 2? Okay. Well, if I do 2 plus 2, that is definitely not less than or equal to 3. All we need is one counterexample. Okay, we found it right here. So this one is not reflexive. And then the third one, A is related to B if A is less than or equal to B. Okay, well, with the equal in there, hopefully it's pretty easy to see no matter what number you pick, every number is always less than or equal to itself because it's equal to itself. Okay, so A is less than or equal to A for all A in the set. Okay, so this one is indeed reflexive. Okay, anti-reflexive just means that, okay, so if we're to take this, it's sort of, instead of for every x in the set, it is related. It's for every x in the set, it's not related. Now we could also write this another way. If we moved this negation out past the quantifier here, and when we move it out there, that quantifier would have to change by De Morgan's law for a quantifier. So another way to write that is that changing this into an existence statement. So here we could say, you know, for every x in the domain, x is not related to itself. Or we can say there doesn't exist a single x in the domain that would in which x is related to itself. You know, these are just two ways of saying the same thing. All right, so let's look at a couple examples. So let's say A was related to B if A was greater than B. Okay, so it is true that we are never going to find any element that is going to be greater than itself, right? So there, or we could say for every element, okay, in the set of real numbers, there's no possible way for an element to be greater than itself. Okay, so for all x that are real numbers, okay, x cannot be greater than x. So this one is anti-reflexive. Okay, similarly, if I find, can I find an element that's where the difference between that element and itself, the absolute value of that is going to be greater than 0? Okay, well, no. We know that if I take A minus itself, I'm going to get 0. The absolute value of 0 is 0, and 0, there's no possible way for 0 to be greater than 0. Okay, so we could say there does not exist an element x in the set A such that x minus x is going to be greater than 0. And that's because, okay, the absolute value of x minus x equals 0, and that's never going to be greater than 0. Okay, so both of these are examples of anti-reflexive relations. Now, if we think about our representations that we looked at, ordered pairs, we looked at digraphs, we looked at matrices. So let's look at how we could, from a list of ordered pairs or from a digraph or from a matrix, determine whether a particular relation was reflexive or anti-reflexive. Okay, so let's go first to the ordered pairs. So if I want to find out if it's reflexive, well, remember, reflexive means that something is related to itself. So I would expect to see pairs like this. Like here, this shows me 1 is related to itself. Okay, I don't see 1 being related to itself up here. Okay. And those would be the kinds of things I'm looking for to be reflexive. So to be reflexive, okay, so we could just ask ourselves, does the pair XX exist for every x in the domain? We'll just say the domain is A. Okay, if yes, it's reflexive. If no, then it's not reflexive. For anti-reflexive, we would just ask ourselves, okay, either, yes, well, does the pair XX never exist for any x in the domain? Okay, and if it never shows up, then it's anti-reflexive. If we see even one time that it shows up, then it's not anti-reflexive. So let's go through these examples. There's 1, 2, 3, 4 different examples here. Okay, so here the pair 1, 1 does not exist. So right now I can automatically say that it's not reflexive because it doesn't show up for every x. So this one is not reflexive. Okay, does it never show up? Okay, well, 1, 1 isn't there, 2, 2 isn't there, 3, 3 isn't there, 4, 4 isn't there, and 2, 3, and 4 are the only vertices there are. It never shows up, so this one is indeed anti-reflexive. Okay. For the next one, okay, does it exist for every single x in the domain? So this one has 1, 1, it has 2, 2, it has 3, 3, and it has 4, 4. Every single one of them shows up, so this one is reflexive. Okay, and it's not anti-reflexive because if I have even one of them, which I do, I have more than one of them, so it's not anti-reflexive. Okay. And now this one goes from 1 to 7, so we're going to have to look for 7 different pairs. We've got 1, 1, we've got 2, 2, and 3, 3, 4, 4, 5, 5, 6, 6, and 7, 7. Okay, all of them show up, so this one is reflexive, and it's not anti-reflexive. And then our last example, all right, I've got 1, 1, I've got 2, 2, I've got 3, 3, 4, 4, 5, 5, and 6, 6. So this one is reflexive, and it is not anti-reflexive. Now notice that here, this one was not anti-reflexive, anti-reflexive. This one is reflexive, not anti-reflexive. Okay, there's never a way that you could make something both anti-reflexive and reflexive at the same time. If it's reflexive, you've got at least one, so certainly it's anti-reflexive. However, there's no example here, but we could have something where it's neither anti-reflexive nor reflexive. So it might not be, it can't be both at the same time, but it can be neither. So for example, if we had like, that 1, 1 and 2, 2 showed up, but 3, 3 and 4, 4 didn't show up, okay, it wouldn't be reflexive because we'd only have 2 out of the 4 possible pairs that would have to make it reflexive, but it also would be not anti-reflexive because if we have at least one place where it is related, then it's not. Okay, so that's an example. Like, we don't have any right here, but that would be an example where it would be both not reflexive and not anti-reflexive. So it can't be reflexive and anti-reflexive at the same time, but it might be neither of them at the same time. All right. Moving on to the digraph representations. Now these digraphs are just the same as these, so we should get the same answers. But something being reflexive is pretty easy to see on a digraph because you're going to see this self loop right here. So if you see a self loop, you know that one's related to 1. Over here we see no self loop, so 1 isn't related to 1. So the questions that we ask ourselves here, okay, is there a self loop at every vertex? If so, it's reflexive. Okay, for anti-reflexive, we would ask ourselves, are there no self loops? Okay, if there isn't a single self loop, then it's anti-reflexive. If there's even one self loop, then it's not anti-reflexive. Okay, so this one is real quick. No self loops. This one is anti-reflexive. Okay, if it's anti-reflexive, it's certainly not reflexive. Okay, here, all self loops all around. So this one is reflexive. If it's reflexive, it certainly is not anti-reflexive. Okay, this one has 7, and there's 1, 2, 3, 4, 5, 6, 7 self loops, so this one is reflexive. So it can't be anti-reflexive. And here, self loops all around. Again, it's reflexive. So it's not anti-reflexive. Okay, so you can see this representation is a pretty easy to, probably a lot quicker to visually determine whether or not it's reflexive or anti-reflexive than the list of ordered pairs. Now let's look at the matrices finally. Okay, if we wanted to know if an item was related to itself, like 1 related to 1, 2 related to 2, okay, that 1, 1 is here, 2, 2 here, 3, 3, 4, 4. We're looking at the diagonal. So the things that we would have to ask ourselves, okay, is the diagonal all ones? If it's all ones, it's reflexive. How could I tell if it was anti-reflexive? We'd ask, is the diagonal all zeros? Okay. So for this one, all zeros along the diagonal. This one is anti-reflexive. So of course it's not reflexive. This one, if I look along the diagonal, it's all ones. So this one is reflexive, not anti-reflexive. This one, 1, 1, 1, 1, 1, 1, 1, 1. This one is reflexive. So of course it's not anti-reflexive. And then this one, 1, 1, 1, 1, 1, 1. This one is also reflexive. So it's not anti-reflexive. Okay. So as far as which representation is most convenient, you might think digraph, you might think the matrix. I think they're both pretty quick, but definitely probably not the list of ordered pairs. Like that, you have to definitely go through every single one. It's a lot harder to find in there. So the digraph or the matrix are probably easier. I think that the digraph visually is easiest to see most quickly, but I'm sure you could make an argument for the matrix as well. Okay, so that's our first set of properties, reflexive and anti-reflexive. The next set of properties we want to look at is symmetric and binary symmetric relations, symmetric binary relations. Okay, so a relation is symmetric if for any elements x and y, they don't necessarily have to be different, they could be the same, but any elements from the domain x and y, if x is related to y, then you also have that y is related to x. Okay, so both of those, either they both show up or they don't. So this is like a, biconditional. And for the biconditional to be true, remember that either these are both true or these are both false. So that's what we see down here. So a relation is symmetric if one of these holds for every pair. So either they're both there, x is related to y and y is related to x. That's where these are both sides are true. Okay. Or neither x is related to y or y is related to x. So that the pair doesn't show up either where. That would make both sides false. So either one of those would make the biconditional true. Okay, so let's look at an example. Okay, let's say we had a binary relation of all the people, all the students in the class, and x is related to y if x and y live together. Now, I'm not there to ask you, but, let's say there's some roommates in the class. Usually there are. There's usually at least one pair of roommates in the class. So let's say that there were some roommates in the class. Okay, so if, certainly is every person related to themselves? Or do you live with yourself? Yes, you live with yourself. Okay, so we always have that every x is related to itself. So if x is related to x, that's automatically, if x is related to x, then x is related to x. So that's what works out for every person. And then if there were any pairs of roommates, if x lived with y, then y certainly would live with x. You can't live with somebody and them not live with you. Okay. And then for all other people, if x didn't live with y, then y certainly didn't live with x. Okay, so this is symmetric. Okay. So if x lives with y, then y lives themselves with X. And that's always true. That implication. Okay. And then what about if X and, so X is related to Y if X and Y have the same parents? Okay. I don't believe there are any siblings in our class. Okay. So everyone is related to themselves. I mean, everyone has the same parents as themselves. But I don't believe there are any students in the class that have the same parents as another student. Okay. So is it symmetric? It's still symmetric because we either have, you know, X is related to itself, so X is related to X and X is related to X, okay? Or we have a situation like this where X and Y don't have the same parents and Y and X also don't have the same parents, okay? So this one is also symmetric. Okay, in particular, I don't think. Anybody has same parents as anyone other than themselves? Okay. And then finally, okay, if X is related to Y, if X and Y have the same major. I'm pretty sure everybody in the class has the same major, okay? And if there was someone in there that didn't have the same major, we still have the case that if, you know, X has the same major as Y, Y certainly has the same major as X. So this one is also symmetric. Okay. Now, just like we can have a reflexive and anti-reflexive, we have symmetric and anti-symmetric. Okay, so a relation on a set A is anti-symmetric if and only if for every X and Y in the domain, as long as X and Y aren't equal, then it's not the case that both X is related to Y and Y is related to X at the same time. Okay. Now this one's just a little bit trickier because there's 3 ways to make this statement true. Okay. So the 3 ways are, okay, if we could have this, like one of them be true and the other one not be. Okay, so X could be related to Y, but Y is not related to X. Okay, or we could have like the swap. Okay, X is not related to Y, but Y is related to X. So notice in either of these we have, okay, exactly a one-way relationship between X and Y, either from X to Y or from Y to X, but not both. The third way to make this true is for neither of them, for them, you know, both of these things to be false. If these are both false, then not false and false would be true. Okay. So we could have either one false, or 2 falses in there to get that statement to be true. Okay. All right. So this is where it gets a little bit tricky. So can a relation be both symmetric and anti-symmetric? The answer to that question is yes, they can be. So remember when we looked at reflexive and anti-reflexive, there's no possible way for a relation to be both reflexive and anti-symmetric at the same time. However, it can be true that a relation is both symmetric and anti-symmetric at the same time. And the easiest example of that is like I'll just do a little small one. Like let's say we have just, you know, 3 items and all we have is self loops. Okay. So notice that the definition for anti-symmetric says if X is not equal to Y. So we don't ever consider X and Y being the same. Okay. So basically, we'd throw out all the self loops and just look at the other edges. Okay, so do we ever have X is related to Y? So what in this particular instance, as long as X and Y aren't the same thing, we never have a relationship between X and Y. X isn't related to Y, Y isn't related to X. We never have like a 1 and 2, 1 and 3, 2. There's no relation between 1, 2, and 3. Okay, so this will be true every single time. So it is anti-symmetric. Okay, but it's also symmetric because every time x is related to y, like 1 is related to 1, okay, then y is related to x, 1 is related to 1. So if all I have is self-loops, that's still symmetric. So these are both symmetric and anti-symmetric at the same time. All right, let's look at those same relations there and look at that. So for if x and y live together, so let's say, I'm not sure, but suppose we do have roommates. Suppose there is at least one pair of roommates. Okay, so if we do have at least one pair of roommates, okay, certainly everyone lives with themselves, so we'll have situations like this. But if we have a pair of roommates, like one person, student 1 and student number 2, we would have like student 1 lives with student 2 and student 2 lives with student 1. Okay, definitely symmetric, but as long as if we have both of those situations, then it will not be anti-symmetric. So this one, if there is a pair of roommates, then this would be not anti-symmetric. Okay, looking at the next one where x and y have the same parents. Okay, let's assume there's no siblings. Okay, and so in this particular instance where we don't have any people with the same parents, we would get a graph that kind of looks like this. Everybody has the same, you know, parents as themselves, but they don't share parents with another person in the class, so you're not going to have any arrows between any of them. So we'll have a situation that looks like this. So this one is anti-symmetric. Now if we can look at this, you know, notice here it was symmetric and anti-symmetric at the same time. Okay, here this one was symmetric, okay, but not anti-symmetric. And then the last example, having the same major, okay, every possible pairs, okay, are in there. Okay, every student has the same major as all the rest of them. So we would have, you know, 3 is related to 1, 1 is related to 3, 1 is related to 2, every single possible thing in there. So this one is certainly not anti-symmetric. Okay. So here, you know, symmetric, not anti-symmetric. The first one, symmetric, not anti-symmetric, but that doesn't always happen. Okay, so we can have this where they're both anti-symmetric and symmetric at the same time. Okay, not true for a reflexive, but true for symmetric. All right, so let's look again at the representations in terms of ordered pairs, graphs, and matrices, and how could we tell from any of those if it was symmetric or anti-symmetric, and which one is going to be the most convenient. Okay, so for reflexive, in the ordered pairs, we'd have to look up, like, so so for all pairs A, B, we'd have to ask ourselves, does BA also exist? Okay, and go through every single pair and just kind of check them off. Okay, and then for being anti-symmetric, so this is for symmetric, so to be anti-symmetric, okay, so we just have to look if AB exists, okay, does BA not exist? All right, so let's go through and look at an example. All right, so here I have 1, 2. All right, so if it's going to be symmetric, then I'd also have to have 2, 1. Okay, I don't see 2, 1 anywhere, so no. For all AB, does BA exist? For this one, the answer is no, so this one is not symmetric. Okay, so for this one, I find a pair and make sure that if that one exists, then if I turned it around, that one's not there. Okay, so for 1, 2, does 2, 1 not exist? There's no 2, 1, so it works for that one. Okay, 1, 3, does 3, 1 not exist? Nope, it's not there. It works for that one. For 1, 4, does 4, 1 exist? Nope. Alright, so that's good. 2, 3 exists. Does that mean there's no 3, 2? There's no 3, 2. That one works. And there's 4, 3. Does that mean 3, 4 doesn't exist? There's no 3, 4. Okay. So, for every AB that existed, BA did not exist. That worked out every single time, so this one is anti-symmetric. Okay. So, symmetric. Okay, so if 1, 1 exists, then 1, 1 exists. Like for all of this, the ones that are self loops, that's going to work out. All right, so 1, 1 is there. Okay, I'll do this in red. All right, is for 1, 3 and 3, 1 are both there? Yep. 2, 2 and 2, 2, yes. 2, 4 and 4, 2, yeah, both of those are there. 3, 3 and 3, 3, yes. 4, 4 and 4, 4. So every time we found AB, we also found BA. All right, so this one is symmetric. Okay. Is it also anti-symmetric? So for AB, does BA not exist? As long as, okay, this is for A not equal to B. Okay, so for like 1, 3 and 3, 1, so we found an A and B that are different, that both exist, so this one is not anti-symmetric. Okay. Alright, the next one. Alright, all of the 1, 1, 2, 2, 3, 3, 4, 4, we'll just check those off. Okay, are 1, 2 and 2, 1 both there? Yes. 3, 4 and 4, 3? Yes. 5, 6 and 6, 5? Yes. 5, 7 and 7, 5? Yes. 6, 7 and 7, 6? Yes. So that takes care of everything. So every time we found an AB, there was a BA. So this one is symmetric. Okay, and did we ever find an A not equal to B where this wasn't true? Well, certainly. There was a bunch of times, like 1, 2 and 2, 1. They're not the same thing, and they're both there, so this one is not anti-symmetric. Okay, and then the last one, we've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. What about when I have 1, 2, do I have 2, 1? No. Okay, so it fails there. So this one is not symmetric. Okay. And then let's look at, alright, as long as A is not equal to B, so ignore all of the 1, 1, the 2, 2, the 3, 3, the 4, 4, the 5, 5, and the 6, 6. So as long as A isn't equal to B, can we ever, as long as we find an AB, is it true that there's not a BA? So there's a 1 and 2. Is there no 2, 1? No 2, 1. So it works for anti-symmetric. There's a 2, 3. Is there also a 3, 2? No. So that one's good. 3, 4. Is there a 4, 3? Nope. So that one's good. 4, 5. Is there a 5, 4? No. 5, 6. Is there a 6, 5? 6, 1, is there a 1, 6? Okay, no. So it's always true that as long as A is not equal to B, when I find AB, I can't find BA. So this one is anti-symmetric. Okay. All right, so how would we go about finding them in the graphs? So for symmetric, okay, basically we'd have to find that, you know, if I have an A and a B, if I can go from A to B and there's an edge that way, I would also have to have one coming back. Okay. Okay, so does this configuration exist? For all, okay, for all edges. All right, so if I find an edge like that, is there a matching one coming back in the other direction? That's the question. All right, and then for the anti-symmetric, okay, I can have this A to B, okay, or this B to A, or I can have nothing between them at all, but never that, right? So this is symmetric. I have this. Anti-symmetric is I have these. You notice that as long as for that one, this one could also have, you know, nothing like this. Okay. So symmetric is just if there exists an edge this way, then there's another one coming back. If there isn't one going, you don't need it. So both of these, okay, situations, we have one of these two situations to make it symmetric. For anti-symmetric, we have to have one of these three situations. And because there's an overlap here, if this is the only situation ever, then it will be both. Okay, so let's look. All right, for this one, I have an arrow going from 1 to 4. Do I have another one coming back from 4 to 1? No, I don't. All right, I don't have this situation, so it's not symmetric. Okay. Now, is it true that for every single edge, it only goes one way or the other, or there's none at all, but it never comes back? Okay, so this one, there's never a pair coming back. This one, there's never a pair coming back. This one, there's not. So no matter what edge I go to, there's never one coming back. So this one is anti-symmetric. Okay, for this one, ignore the self loops, because I'm only looking for A not being B. Okay, and when A is not, so I can ignore those and just look at the edges in here. So I've got a pair here, and I've got a pair here. Okay, every time I have an edge, I've got the one coming back. All right, so this one is symmetric. Okay, and it's definitely not anti-symmetric because I have pairs that are coming back. So this is not anti-symmetric. Alright, for this one, you can ignore all of the self loops. Okay, self loops are not, those will make it symmetric. Okay, so I have this pair, I have this pair, I have this pair, I've got this pair, I've got this pair. So every time I have one, I have the matching one coming back. So it is symmetric. Okay, and I have at least one pair where their two sides aren't the same, so it's not anti-symmetric. And the last one, ignore the self loops. Okay, I have 1, 2, but I don't have 2, 1. All right, so I don't have this for every single edge, so this one is not symmetric. And then, okay, I've never got a pair. I have 1 to 2, but not 2 back. I have 2 to 3, but not 3. I have 3 to 4, but not 4 to 3. I have 4 to 5, not 5 to 4. I've got 5 to 6, not 6 to 5. I got 6 to 1, but not 1 to 6. So I never have a pair of them. I only have A to B or B to A or nothing. So this one is anti-symmetric. Okay. All right, now let's look at the matrices and think about, all right, so I can just kind of ignore them. So if I had zeros or ones or any collection of zeros and ones, that's not really going to make a difference. Okay, so if I just go and kind of knock out the diagonal, And then think about, all right, well here, this one is 2, 1. And if I go directly across, if I sort of fold this across the diagonal, this 0 would land on top of this 1. Okay, so this is 2, 1, and this is 1, 2. So I would look across the diagonal, okay, if I fold it over there, and see every time I have a 1, do I have a 0 on the other side? Okay, that would be anti-symmetric. And here, if I had a situation like this one, where I look across, there's a 0 here and a 0 here, a 1 here and a 1 here. This 0 would fall on top of that 0. This 0 would fall on top of that 0. Okay. If I fold over the diagonal and the sides always match, then it's going to be symmetric. There's sort of symmetry over the diagonal. So for this symmetry, sort of, fold over the diagonal. And if the sides always match, then it's symmetric. Okay, and for anti-symmetric, okay, so if you fold over the diagonal, then all 1s fall on 0s. Okay. The 0s can fall on 0s as well, but it's just most important that all the 1s fall on 0s. Okay, so here, this 1 would fall on a 0. 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 Okay, here we have a 0 that falls on a 0. That's fine. Okay, I just am concerned about the 1s. 1 falls on a 0. So this one is anti-symmetric, because every 1 falls on a 0. Okay. Do the sides always match? No, because we had 1s falling on 0s, so this is not symmetric. Okay, for this one, when we fold over, the 0 falls on 0, 1 falls on 1, 0 falls on 0, 0 on 0, 1 on 1, 0 on 0. All the sides match, so this one is symmetric. Okay. Did we have 1s that fell on 0s? No, we had 1s that fell on 1s, so this one is not anti-symmetric. Okay, this one. Okay, do the sides always match? Now, it's kind of easiest to just look at the 1s. Okay, this one matches this one. This one matches this one. This one matches this one. This one. All right, and since everywhere else is 0s, yes, they're going to match. They're going to fall on each other. Okay, so everywhere they match, so this one is symmetric. It fell on 1s. 1s didn't always fall on 0s, so this one is not anti-symmetric. And then this last one. Okay. Here, a 1 fell on a 0, a 1 falls 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 on a 0, and a 1 falls on a 0. Okay, so when we folded over the diagonal, we always got the 1s to fall on 0s. And so this one is anti-symmetric. Okay, and they didn't match because 1s and 0s got paired up, so this is not symmetric. So in terms of which one representation is most convenient, it probably just sort of depends on the size and how many. I think, certainly it was not the ordered pairs, right? So it's pretty easy to see in the digraphs, also fairly easy looking across the diagonal. I think you could make an argument for either of these, but I think in any of these, we're never arguing for the ordered pairs being the most convenient for testing. Okay. The next relationship are transitive binary relations. And so a relation is transitive if it's true that for every x, y, and z, if x is related to y and y is related to z, then this y is sort of a connection between them, and then we'll get that x is related to z. So x related to y and y related to z implies that x is related to z. That will be a transitive relation. All right, so which of these relations on the set of integers is transitive? Okay, so would it be the case that is it always true that if x is related to y and y is related to z, will that imply that x is related to z? Okay, is that true? Well, what does that mean? So x is related. So here, if x related to y is true, that would mean x is less than y. Okay. And if we had that y was related to z, then y would be less than z. Sorry, I put that in there. Okay. So if x is less than y and y is less than z, is that automatically going to give us that x is less than z? Well, yes. Okay, that's the way the Leslian operator works. So that will always be true for every possible pair of integers. If x is less than y and y is less than z, it will certainly be the case that x is less than z. So this one is transitive. Okay. Let's say x is related to y if x divides y. So is it true that if x divides y and y divides z, can I automatically conclude that x is going to divide z? All right. Well, let's think about what that means. So if x divides y, that means that y is 2 times some integer a. Okay, if y divides z, that means that z is, why did I say 2? It's x times some integer a. Sorry about that. Z is y times some integer b. Okay, and then we could take this x times a and substitute it in for y over here. So we would get z is x times a times b. Okay, so does x divide z? Well, can z be written as some integer times x? Well, if a and b were both integers, then this right here is an integer times x to get z. So yes, indeed, this will be true. Okay, so this one is also transitive. All right, and then the last one, all right, if x is related to y, if x equals 2 times y. Okay, so do we have, if you know, x equals 2y, that's x related to y, and then y related to z would mean that y is equal to 2 times z. And then would that give us that x is related to z? All right. So let's see. So for example, here I could have like 8 is related to 4 because 8 is 2 times 4. And then our y is 4. 4 is related to 2. Because 4 is 2 times 2. So does that mean that 8 is related to 2? Okay, so here's 4, kind of the middleman. So 8 is related to 4, 4 is related to 2. Is 8 related to 2? Is 8 2 times as big as 2? No. So this one is not transitive, because we found at least one counterexample. Okay, it would only be transitive if it's always true. If I can find one counterexample, then it's not transitive. Okay. So we've got two more examples to look at. So this time we're going to look at every single property that we've discussed. So we've got look at two positive integers. They are relatively prime if their only common factor is 1. Okay, so let's just kind of make sure we understand this before we look at this relation and decide if it's reflexive, anti-reflexive, symmetric, so on. Okay, so the factors of 5 are just 1 and 5. The factors of 11 are just 1 and 11. So their only common factor is 1. Okay, so 5 and 11 are relatively prime. Okay, and they're also both prime, so maybe it makes sense that they're relatively prime. Are 10 and 25 relatively prime? Okay, well the factors of 10 are 1, 2, 5, and 10. The factors of 25 are 1, 5, and 25. And so they both have 5 as a common factor. These are not relatively prime. They are also not prime numbers, so maybe that makes sense. Okay. Now if we look at these two, 26 and 33, the factors of 26 are 1, 2, 13, and 26. The factors of 33 are 1, 3, 11, and 33. Now, neither of these are prime numbers, but their only common factor is 1. So these two numbers are indeed, these are called relatively prime. They don't share any factors besides 1. So they doesn't mean that the numbers are prime, just with respect to each other, they are relatively prime. Okay, so that's relatively prime. So let's say we defined a relation on the positive integers. So x is related to y if x and y are relatively prime. Okay. So first of all, is R reflexive? This would mean that every number would have to be relatively prime to itself. Okay. So is, 2 relatively prime to 2? Okay. No. Because 2 and 2 also share the common factor of 2. So this is not reflexive. Is it anti-reflexive? Is it true that I will never ever be able to find any positive integer that is related to itself? Well, 1 is related to 1. Yes, the only common factor between 1 and 1 is 1. So 1 is related to itself. So is it anti-reflexive? No, it's not anti-reflexive. Okay. So 1 is related to itself. After that, 2, 3, 4, 5, forever on. Okay, all of those will be not related to themselves. But since we don't have that it's always true or that it's always false, it's neither reflexive nor anti-reflexive. All right. Is it symmetric? Okay, so if x is relatively prime, okay, so if x and y only have 1 as a common factor, then y and x only have 1 as a common factor. Okay. There's no way for x and y to have something other than 1 as a common factor, but y and x not have something, right? So if these have to be true at the same time. So yes, this one is symmetric. Is it anti-symmetric? So when x is not equal to y, if I have x and y, x is related to y, will I not be able to get y is related to x? No, definitely not. We're always going to have xy and yx, both pairs in there. Okay, so this one is no. And then is it transitive? So if x is relatively prime to y, so let's write this. So x related to y and y related to z, is that going to give us that x is related to z? Okay, so let's say we have, let's say 10 is relatively prime to 21. Okay, so this has just the factors 2 and 5, 1, 2, and 5, and 10. This just has the factors 1, 3, 7, and 21. So 1 are the only things that are in common. And then 21, let's see, that's relatively prime with, so let's say 35. So this one has just 1, 3, 7, and 21. 35 is just 1. Oh, that's not 35. Like I choose a different one. Because that had 7. Let me do 2 times. Let me do 14. Sorry. Okay, so 21 and 14. That's the 14s only are 1, 2, 7, and 14. Oh, I keep choosing the 7. Okay, it has to not have a 7 or a 3 in it. Let me do 2. Okay, let's do 1 and 2 because I wanted to share something over there, but it can't have a 3. I mean, I can't have a 5. Oh, it could have a 5. Here, maybe let's make this one. We can make it 5 and another 2. Okay, so let's maybe that would be 20. 20 and 21. We finally got it. Okay. So this has 1, 3, 7, and 21. 20 has 1. It has 2. It has 5. And it has 20 as prime factors. Okay. And also 4 and 10, I guess, if you wanted to list all the other factors in there. But the only ones that are in common are 1. So these are relatively prime. So does that mean that 10 is relatively prime to 20? Well, certainly not. So this one has factors 1, 2, 5, and 10. This has 1, 2, 5. Okay, 10, 20, oh, it has a 4 as well. Lots of common factors like 2 and 5 and 10. Okay, so this one is a definite no. So this one is not transitive. Okay. Sorry, it took me a while to get there. The goal, we just had to find something where these two don't share any factors, these two don't share any factors, but these two did share factors. Okay, and our last example, we've got several examples, so we'll just go through every single one of them, try to get through them quickly. Alright, so we've got a relation that's defined on the set of real numbers. X is related to y if the sum of the two numbers is 0. For example, like -2 and +2 would be related because their sum is 0. Okay, so the question, is it reflexive? Well, for it to be reflexive, then it would have to be true that every time I take a number and add it to itself, will I get 0? So is x plus y equal to 0 for every x? Certainly not. So it's not reflexive. Is it anti-reflexive? Okay, well, is it true that if I take, sorry, this should be an x over here. If I take an x and add it to itself, will I always get 0? No. Okay, if I take an x and add it to itself, will I never ever get 0? No matter what x is. Well, that is also a no, because 0 plus 0 equals 0. So 0 is related to itself. That's the only one, but there is one. Okay, so this is not anti-reflexive. It's neither. Okay. Is it symmetric? Okay, so if x plus y is equal 0, will I automatically get that y plus x is also 0? Well, this one is yes, because addition is commutative. Okay, so if I add it in this order and get 0 and add it in the other order, it's still going to be 0. Those will both have to be true at the same time. Okay, so this one is symmetric. Is it anti-symmetric? Okay. Well, no. So is it never true that that if 2 is related to -2 and -2 is related to 2? We're definitely going to have non-equal values where I've got both relations. So this one is not anti-symmetric. Is it transitive? Okay. So if I have that, x plus y equals 0 and y plus x equals 0, is that going to give me that, sorry, x plus z equals 0, is that going to give me x plus z equals 0? Okay. So, for example, we'd have to have the same y, so let's say this was 2. Okay, well, the only way for that to be true is if this is -2, and the only way for this one to be true is if this is -2. Okay, so I have -2 is related to 2, and 2 is related to -2. So does that mean -2 plus -2 equals 0? No. Okay, so this one is not transitive. Alright, let's look at the relation on the set of positive integers. Okay, x is related to y if y divides x. So is it reflexive? Okay, is it true that x is always related to itself? Well, x would be related to itself if x divides x. Well, x divides x for every positive integer. Okay, so it is reflexive. Is it anti-reflexive? Okay. Can we never ever find an x that divides itself? Well, no, certainly that's not going to be true, so it's not anti-reflexive. Is it symmetric? Okay, so if x is related to y, I guess we have y divides x. So y divides x, does that automatically give us that x divides y? Okay, certainly not. No, so for example, 2 divides 4, but 4 doesn't divide 2, right? 3 divides 9, but 9 doesn't divide 3. So we're not going to have it going both ways. So this is not symmetric. Is it anti-symmetric? Okay. So for every pair of numbers where they aren't the same, so as long as x and y is not the same, okay, will we only have x divides y or y divides x, okay, or neither. Okay, so if we had x divides y and they're not, okay, and this is again for x not equal to y. Okay, so if x divides y, then that means that x has to be less than y, and so there's no possible way for y to divide x. Okay, So there's no way for both of these things to be true at the same time. It could be neither. Okay. So, but neither neither of these can be true at the same time. And so this one is anti-symmetric. Okay, so we'll never get both x divides y and y divides x at the same time. All right, and then is it transitive? Okay, so let's say we had x related to y. That means y divides x. So x related to y and y is related to z. If y is related to z, that means z divides y. Okay, and will that, let me write these above here so that we're not, okay, so this one is x related to y, this one is y related to z. Okay, so they're related if the second one divides the first one. So the second one, y divides the first one. The second one divides the first one. Okay, x related to y, y related to z. Is that going to give us x is related to z, so that z divides x. This one we Alright, so this one, we know that that means x is equal to some y times some integer a. And this one, we know that means y is equal to some integer times z. Okay, so here, if we take bz and substitute it in here, we're going to get x equals b times z times a. Or we could group the a and the b together and write that as z times ab. Okay, so does this mean that x is an integer multiple of z? Yes, x is an integer multiple of z. So this one is indeed true. And so it is transitive. Okay, and our last one here, R is a relation on the power set of the set containing 0, 1, 2, 3, and x is related to y if x is a subset of y. Okay, so let's think about what the power set is. That would be the set that has all subsets of size 0, which is the empty set. All subsets of size 1, so that contains just 0, just 1, just 2, just 3. Okay, subsets of size 2, 0 and 1, 0 and 2, yawn and on it goes. Subsets of size 2, subsets of size 3, up and up it goes all the way up to subsets of size 4, so 0, 1, 2, 3. I'm not going to write out all 16 of them because that's a lot, but you remember how the power set goes. Okay, and so I'm going to pick elements out of the power set. So there's 16 different sets in there that I could choose, and the first set will be related to the second set if it is a subset. Okay, so is every set a subset of itself? Yes, every set is a subset of itself. So it's reflexive. Is it anti-reflexive? Okay, would I never ever be able to find a set that is a subset of itself? No, definitely not. Every subset is a subset of itself, so it is not anti-reflexive. Is it symmetric? Okay, so if, for example, 0 is a subset of this one, 0, 1. Okay, is 0, 1 a subset of 0 as well? Does it go both ways? No, it does not. Okay, so this one is not symmetric. Is it anti-symmetric? Okay. So, if x is not equal to y, okay, so will I, if and x is a subset of y, implies that y is not a subset of x. So I can't have both of them, right? As long as, because the only way for both of them to be true is for them to be equal. If they're not equal, I'll never get both of those happening at the same time. So it's definitely anti-symmetric. And then is it transitive? Okay, so if x was a subset of y and y was a subset of z, would x be a subset of z? Well, this means every element of x is an element of y. And this means everything in y, which happens to be that all of the x's are in there, those would all have to be in z. So this one is true, yes, so it is transitive. Okay. All right, so those are the important properties of sets: reflexive, anti-reflexive, symmetric, anti-symmetric, and transitive. Next time we will look at special kinds of relations that have like a subset of these properties and what that and define special relations based on the properties that they have.